periodic Fourier series. So, to start with, if f(x) is any function defined in the interval 0 to 2L, or we can say that C to C plus 2L in general, then first condition is that the function should satisfy the Dirichlet's condition and the function must be periodic. Then only we can find Fourier series for that function. So let's see what are Dirichlet's conditions. So here, if a function f(x) is defined within the interval C to C plus 2L and some more conditions are there. First condition is f(x) is defined and it is a single value. So basically the first condition states that the function should be well defined and it must be a single valued function. The second condition is function should be continuous or finite discontinuity in the corresponding periodic interval. So by the second condition, it means that function should be a continuous function or there should be, it should have finite discontinuities in that given interval. Third condition is that f(x) and f dash of x are piecewise continuous. That means the function f(x) should have derivative. That means we should find derivative for this function. It should be differentiable function. And that derivative also, the function along with its derivative should be piecewise continuous. Now, these are the Dirichlet's conditions. As I stated earlier, if the function is periodic and it satisfies this Dirichlet's condition, then we can find Fourier series for that function. Okay. Now, here some examples are written over here. So, let's see this. f(x) is equal to tan x. Suppose this function tan x is defined in the interval 0 to pi. Now we know that pi by 2 obviously lies in this interval 0 to pi. Now when we consider x is equal to pi by 2, this particular value, then this function f(x) will become tan pi by 2, which is the infinity. So this is not a well-defined function. And that means we cannot find Fourier series for this particular function in this particular interval. We cannot find Fourier series for tan x in the interval 0 to pi. Second example is, if we define f(x) is equal to sine inverse x. Now this sine inverse x is a multi-valued function because we can see this sine inverse 0. Now sine inverse 0 will have 0 value, pi, 2 pi, 3 pi and so on. In general it is n pi for n positive integers. So this is a multi-valued function. This is not a single valued function, so which contradicts to this condition number 1. And therefore we cannot find Fourier series for this sine inverse x also. Now let's move to definition of Fourier series. So if f(x) is a periodic function defined in the interval C plus 2L and which satisfies all Dirichlet's conditions, then we can express f(x) as summation in terms of cosines and sines, and that is nothing but a Fourier series. So definition is f(x) is equal to a naught by 2 plus summation n running from 1 to infinity of an cos n pi x by L plus bn sin n pi x by L. Now here it is very important to get these coefficients a naught, an and bn, and of course we are having the integration formulas for finding the coefficients. A naught is equal to 1 upon L integration within this interval C plus 2L of the function f(x) dx. So this is the formula to get a naught. An is equal to 1 upon L integration over the limits C plus 2L of f(x) into cos n pi x by L into dx, and bn is equal to 1 upon L integration C plus 2L f(x) into sin n pi x by L dx. So these are the formulas or formulas to find the coefficients in this Fourier series. Now see the interval c plus 2l. So generally we are taking value of c as 0 or it may be minus 5. Now suppose we are taking c equal to 0 value, then this interval becomes 0 to 2l. Right? Only you have to substitute c equal to 0 here. So the interval becomes 0 to 2l. And at the same time, if we are replacing L equal to pi, then this interval becomes 0 to 2 pi. Right? So for the interval 0 to 2 pi, this particular theta, that means here you can observe that n pi x by L term is there. So n pi x by L. We are substituting L as pi. So this becomes n pi x by pi. Pi becomes cancelled out and this will be n. Right? So value of c, it may be value of c, we may take this as 0 or value of c, it may be minus L. So these are the formulas for coefficients and this is the formula of Fourier series. Now let's move to one example. Let's take one example here. Suppose example is find Fourier series for fx is equal to, let's take function x defined in the interval 0 to 2 pi. Right? So here, let's write formula first. Fx is equal to, the formula of Fourier series is a naught by 2 plus summation am cos n pi x by L plus bn sin n pi x by L, where n running from 1 to infinity. Right. Now here the interval is 0 to 2 pi. So whenever we are taking 0 to 2 pi, that means we are going to compare this with 0 to 2L. This implies value of L is pi and therefore our theta value, that means n pi x by L becomes n pi x divided by pi. Pi will get cancelled out and this will give you nx. Right? Now let's remember this nx. Now formula of a naught is equal to 1 upon L integration of, now here whatever given interval is given, we are going to write that as a limit 0 to 2 pi. And of course, the thing is L equal to pi. So let's write here only L is equal to pi. So the formula of A naught becomes 1 upon pi integration 0 to 2 pi f of x du. So now let's calculate this integration. 1 upon pi integration 0 to 2 pi. Value of function is x into du. So it becomes 1 upon pi integration of x is x square by 2 within the limit 0 to 2 pi. Right? So this 1 upon pi as it is, put upper limit is 2 pi. So x square becomes 2 pi square. Let's write this. 2 pi square is 4 pi square divided by 2 minus lower limit becomes 0 because 0 square is 0. And you can see this. Therefore, a naught is equal to, see this value. Here, this pi will get cancelled with this and 2 is 4. So value of a naught is 2 pi. Okay. Now, let's find an. Here in the Fourier series, we are just going to apply the formula. The formulas are very important. Formula for an is 1 upon pi, because of course L is pi, so 1 upon L becomes 1 upon pi. Integration of 0 to 2 pi f of x into cos n pi x by L. So earlier we have seen that n pi x by L is nx. So I'm writing cos of nx dx. Therefore, now what we have to do? Put value of fx. So this an becomes 1 upon pi. Upper limit, lower limit. So it is upper limit is 2 pi, lower limit is 0. Fx is x into cos nx dx. Now how to solve this particular integration? So we can go with integration by part method while calculating the integration. So here an is equal to 1 upon pi will be as it is. X we are writing as it is into integration of cos nx. Integration of cos nx is sin nx upon n, right? Minus derivative of x is 1 into integration of this bracket. So integration of sin nx is minus cos nx divided by n square. I have applied integration by parts generalized rule, and the next term becomes derivative of this 1, which is 0. So we have applied this formula. I am writing here integration uv dx, integration by part generalized rule. This is u v1 minus u dash v2 plus u double dash v3 and so on. So let me explain this one more time. This is our u function and this is our v function. So first step is u v1. So I have written x as it is. V1 means integration of this term. Integration of cos nx is sin nx upon n. Now, next term is u dash into v2. That means we are proceeding with derivative of this term, integration of second term. So derivative of first term, that is x is 1, and integration of the bracket is minus cos nx upon n square. Now plus, see, you can see here alternate plus minus sign is there. So we are writing here plus sign now, and derivative of this first term, integration of the second term. So obviously derivative of this one is 0. So now onwards the term will be 0. So this is the formula for integration by part generalized rule. So now let's move to our actual example. After writing integration by part generalized rule, write the limits, because we are going to calculate the integration within the limit. This is a definite integration. So it's 1 upon pi as it is. Now here we can see that whenever we are going to substitute upper limit, this becomes, let's put the value, x is equal to upper limit 2 pi, and now sine of n, x is equal to 2 pi upon n. Minus minus becomes plus sign, cos of n 2 pi upon n square Right? This is the upper limit. Now put lower limit. Lower limit is 0. So this term becomes minus of x is equal to 0. So just I'm writing 0 because x into anything, 0 into anything becomes 0. And minus. Now see the sign carefully. For upper limit, we have written whatever signs are there. And minus lower limit. So this becomes, this sign is minus, minus plus sign. And for lower limit, we are taking negative sign. So that becomes cos of 0 upon n square. Okay. So which is equal to 1 upon pi sine 2n pi. Now we know that sine of n pi is 0 for integer number, and obviously this 2n is an integer number. So sine n pi becomes 0 plus cos 2n pi. Now 2n is an even number, and we have the formula of cos n pi. Let me write the formula here. Cos of n pi is equal to minus 1 raised to n. Right. So whenever we are taking even number, we'll get plus 1. And whenever this n is odd, we will get minus 1. Now in this example, we are taking cos of 2n pi, which is an even number. Therefore, this becomes 1 upon n square minus this cos 0 is 1 upon n square. So addition is 0. Therefore, we are having value of an is equal to 0. Now we'll continue with the same example. Still we have to find dn. dn formula is 1 upon pi integration 0 to 2 pi f of x into sine of nx d, which is equal to 1 upon pi integration 0 to 2 pi. Function is x into sine nx dx. Now immediately I will write this integration by part rule here. Integration by pi generalized rule. U v1 minus u dash v2 plus u double dash v3 and so on. So which is equal to 1 upon pi. This is our u function. Therefore, u as it is, that means x as it is, into integration of sine nx, which is minus cos nx upon m, minus derivative of first term. So derivative of x is 1. Integration of the second term. So integration of this bracket, I will say. What is the integration of minus cos? Integration of minus cos is minus sine nx upon n square. And then we will get 0 because derivative of 1 will be 0. So that's it. And of course, don't forget to put the limit. Now let's put the limit. So here in the Fourier series, we have to note that whenever the limits are in terms of pi or maybe 2 pi, then the sine of nx, so this becomes sine 2n pi, which will give you 0 value. And see the lower limit is also 0. So sine of 0 becomes 0. So here I will write for upper limit, it will give us 0 value. For lower limit, it will give us 0 value. So we can ignore this term because it is giving 0 value as the upper limit and lower limit. After putting upper limit as lower limit, it becomes 0. So only we have to concentrate on the first term. So see this upper limit is 2 pi. So put x is equal to 2 pi here, negative sign as it is, minus of cos n 2 pi upon n, right? This term is 0. And when we put lower limit, when this x becomes 0, so let me write that minus of lower limit, x is 0. So no need to write rest of the terms because earlier I explained about this term. Sine of 2 n pi is 0 and sine 0 is 0. So that's it, which is equal to 1 upon pi 2 pi. Cos of 2 n pi is again plus 1, and due to this minus sign, it becomes minus 1 upon n. So this pi will get cancelled out, and therefore answer of Bn is minus 2 upon n. Okay. Now let's immediately recollect the values of A naught. So here A naught is equal to 2 pi. An was 0. So let's write that A naught is 2 pi. Let me write here. So here A naught is equal to 2 pi. An is 0 and Bn is equal to minus 2 upon n. And then we are going to use definition of Fourier series, which is fx is equal to A naught by 2 plus summation n running from 1 to infinity An cos nx plus Bn sin nx. We are taking only positive integers. So this is equal to, just we are going to substitute the value of A naught. A naught is 2 pi. So here 2 pi divided by 2 plus summation over the limit 1 to infinity. An is 0 and Bn is minus 2 by n sin nx. So this is the final answer for Fourier series. Pi plus summation n running from 1 to infinity minus 2 by n sin of n. So function x we have expressed as series of sine terms.